Hi, I'm Norman Walberger, and in today's lecture we're going to connect Cartesian coordinates that we talked about last time with our basic notions of this new universal hyperbolic geometry that we introduced earlier. Namely, the notions going back essentially to Apollonius and Pappus of the polar duality between a point and a line with respect to the base circle, and the notion of quadrants and spreads in terms of cross ratios. So we're going to derive three main theorems here. And the first one is the duality and coordinates theorem, then the quadrants and coordinates theorem, then the spread and coordinates theorem. And what they tell us is, first of all, if we have a point, x0, y0, then the dual line is given by this expression, x0 to y0 to 1. Almost the simplest possible thing you can do. You take the two coordinates and you add another 1 for a third component, forming the proportion that specifies a line. And I remind you that our convention for a line is, this is actually a line here. And it's the line whose ordinary equation in x and y is x0 times x plus y0 times y equals 1. And now here is a formula for the quadrants between 2 points a1, a2 in terms of the coordinates x1, y1 and x2, y2 of a1 and a2 respectively. It's quite a pleasant formula. It involves the same kind of term, sort of an x1 squared plus y1 squared minus 1. That pattern repeated there with x2 squared plus y2 squared minus 1 there. And the numerator here is something like it, except that it's x1 times x2 plus y1 times y2 minus 1, and it's all squared. So the quadrant is 1 minus this fraction. And a very similar formula for the spread between two lines. Have one line L1, M1, N1, and another line L2, M2, N2. Then the spread between them is 1 minus this expression. And now there's three things instead of two. We compensate by writing L1, L2 plus M1, M2 minus N1, N2. Now all squared. And that's over L1 squared plus M1 squared minus N1 squared times L2 squared plus M2 squared minus N2 squared. So these two formulas are pretty similar, but they're a little bit different because our lines and our points are a little bit different. Now there's a few things to say about today's lecture. First of all, we are going to have to roll up our sleeves. I've got my sleeves rolled up. And we're going to have to make some calculations. And there's going to be some pleasant simplifications that occur, sort of surprising simplifications, which are typical of the kinds of algebra that appear in hyperbolic geometry in this framework. So we are going to have to do a little bit of crunching with algebra. For those of you who are very familiar with algebra, it will be pretty routine, if a little bit long, and you can kind of just skim over it and verify that I'm not cheating too much in any one place. If you're weaker in algebra, then the manipulations that I'm making will maybe be quite instructive to you. In which case you want to really slow down, have a good look at what I'm doing, and I'm going to give you some examples to try your hand at it yourself. The other thing that I have to mention at this point is that in some sense these formulas are preliminary. They are not ultimately the formulas that we are going to use. They are very well suited for work within the Cartesian coordinate framework, the usual xy plane. But very shortly we're going to step up a notch to the projective plane. And we're going to use homogeneous projective coordinates, whatever they are, instead of these Cartesian coordinates. And so we're going to end up with new versions of these theorems which are going to look a lot the same but slightly different, in which the roles of the points and the lines are much more symmetrical. So even though we're going to be later on moving to this higher level, I think it's good to start here, develop the formulas in the Cartesian setting, and then when we do go to the projective setting, you'll be able to see how the transition looks like, which is quite instructive. How to go from a Cartesian equation to a projective homogeneous equation. All right. So there's a lot to learn here in this video, but if it's a little bit onerous for you, don't worry too much. You can think of it as just being a check to make sure that these three fundamental facts really are correct. All right, so let's start. Our first theorem is the duality in coordinates theorem. We want to express what duality looks like algebraically. So if A is this point here, x0, y0, then the dual line A perp is x0 to y0 to 1. Let's have a look at one or two examples. Here's our unit circle, C, also called the null circle. Here's a point A with coordinates 2, 1. The theorem tells us that the dual line will have coordinates 2 to 1 to 1. In other words, it's a line with the equation 2x plus 1y equals 1. And there's that line right there. And I hope that does look like the dual of the point A. Remember, one way of thinking about it, if the point A is outside the circle, is it's the line formed by the 2 points that you get by joining A to the circle tangentially. Finding the tangents from A to the circle, that would be those 2 points there. We're just connecting them. Here's another example of a point B. It's inside the circle now. It's 0 minus 2/3. According to the theorem, the dual is 0 to minus 2/3 to 1. And that's a line with the equation 0x minus 2/3 y equals 1, or once we multiply by 3, minus 2y equals 3. So that's the line y equals minus 3/2, which is down there in green. And that does look, I hope to you, like the dual line to this point B here. So algebraically, this dual idea is very simple in Cartesian coordinates. It's surprisingly simple and very natural. The main challenge for us is to show that A perp is actually well defined. So I remind you what we did to define the dual. If there's a point A, then what we did is we said, all right, let's choose 2 lines through A which meet the circle in 4 null points. And then looking at those 4 null points as a quadrangle, we look at the other lines that connect those 4 points besides the 2 ones that we've already got. So there are these 4 new lines, and they meet in 2 additional points called diagonal points. There's one down here, and there's one up there. And it's the line through those 2 diagonal points which is then the dual of the point A. And what we have to do, in fact, is to show that this construction is actually well defined. In other words, that if we change the black lines, then, well, all the green lines change, but the resulting dual line is still the same. So this theorem actually is more really than it looks like. We're actually also going to verify that the dual really does exist. What we need now is some technology to allow us to deal with lines created by points on our null circle. Now I remind you that points on the null circle were parameterized by a parameter t, and that we use this notation e of t to represent a point that had a form like this. This was e of t1. What we want to do is we want to get an equation for a line connecting 2 such points. And here's the theorem that we need. The line through 2 null points theorem. Telling us that the line L through E of T1 and E of T2 is this line right here. It's got 3 components. The first one is 1 minus the product T1, T2. The middle one is t1 plus t2. And the third one is 1 plus the product t1 times t2. Okay, so let's start by recalling the parameterization of the null circle. At any point on the null circle, except for -1, 0, okay, which is a little bit exceptional, any other point has this particular form. We call that E of t1. I'll remind you, it's 1 minus t1 squared over 1 plus t1 squared, and 2t1 over 1 plus t1 squared. And we have a similar expression for E of t2. So we have these 2 points on the null circle, and we now want to say, what's the equation of the line that connects them? Well, we know how to write down the equation of any line joining any 2 points. That's the line through 2 points theorem. And if this was x1 and this one was y1 and this one was x2 and this one was y2, then you may recall that that formula was, the first thing is y1 minus y2, and the next one is x2 minus x1, and then the next one is x2 y1 minus x1 y2. And you'll see that that's what we have here. So this is y1, this one here is the y2, here's the x2 minus x1, and here we have x2 times y1 minus x1 times y2. This is a proportion between these 3 things. Well, we want to simplify that. So let's simplify it by multiplying through by the common denominator. The common denominator is the product of 1 plus t2 squared and 1 plus t1 squared, which appears in all of these terms here, at least partially. So if we multiply by that product, then we're going to clear all of these denominators at the same time. And the proportion is not going to change because we're allowed to multiply all the 3 elements in a proportion, leaving it unchanged. So what happens? The first term here, we're going to multiply the top here, 2t1, by 1 plus t2 squared, because the other 1 plus t1 squared will cancel with that one there. Minus 2t2 times 1 plus t1 squared. What happens here? Well, we're going to get 1 minus t2 squared times 1 plus t1 squared. The other term, the other one disappears with that. Minus 1 minus t1 squared times 1 plus t2 squared, because the 1 plus t1 squared gets cancelled. And over here, well, we're just cancelling all of these denominators. We just get 1 minus t2 squared times 2t1 minus 1 minus t1 squared times 2t2. Now at this point, something interesting happens. It turns out that each of these 3 terms has a common factor. Well, the common factor is 2, as well as the term t1 minus t2. So where can we see a t1 minus t2 happening? Well, if you look here, the first expression here and the first expression here, well, that's t1 minus t2. And there's also a 2, so if we drop that out, those will disappear. And then we'll have t1 times t2 squared minus t2 times t1 squared. Well, that's exactly t1 times t2 times this common factor of t1 minus t2, which we have agreed to get rid of. How about over here? Well, if you look at the various terms and expand them out, you expand this thing out, you'll see that the only thing that's left is, so there's 1 minus 1, that cancels. T2 squared or t1 squared cancels with the t1 squared and t2 squared there. The only things that are not around are a t1 squared minus t2 squared from there, and another t1 squared minus t2 squared from there. So 2 t1 squared minus t2. When we cancel t1 minus t2, we're left with the other factor, t1 plus t2. So some of you will not be that comfortable with the algebra. Write it out. Okay? Expand this all out. Make sure you see that when you simplify that, expand it out, you're going to get this term here times t1 plus t2. And similarly over here, you can expand that out. It's the same kind of story as over here. And after you cancel this common factor, you can get 1 plus t1 times t2. This is a very nice expression. The expression for a line going through 2 points on the unit circle, those 2 points having parameters t1 and t2. That's the end of our proof of this preliminary kind of theorem. Now we are going to derive another very useful result that we'll use more and more later on as well. This is the result that tells us if we have 2 lines through the unit circle of the kind we've just established, one through e of t1 and e of t2, and another one through, say, e of t3 and e of t4, then where do those 2 lines meet? So there's L of t1, t2. We're going to make this definition. Let's call this expression, it's the line joining e of t1 and e of t2. Let's call it L of t1, t2. And so there will be L of t3, t4. Same thing. And this is now the what we're interested in, that the meet of interior lines theorem, that these 2 lines here, L of t1, t2, and L of t3, t4, are parallel, first of all, precisely when this condition holds. So it could easily be that those 2 lines are parallel. But if they're not parallel, so otherwise, they meet at this rather imposing looking point. We'll give that a name. We'll say that it's M for meet. M of t1, t2, colon t3, t4. Because it depends on the 2 points 1 and 2, which forming the first line, and the points t3 and t4 forming the second line. And have a look. That's a point. It's got 2 components, the x component and the y component. The denominators of both expressions are the same thing. They're exactly this condition that the line be parallel or not. So when the lines are parallel, the denominators here are both 0, and we're out of luck. Those lines are not meeting in the ordinary Euclidean plane. However, if this condition is not met, then these numbers here on the bottom are not 0, and these are legitimate expressions. And the numerator here looks a lot like the denominator, except for 2 plus signs where there's minus signs below. So that plus sign instead of that minus sign, and that plus sign instead of that minus sign. While the y term looks quite different, its numerator is 2 times t3, t4 minus t1, t2. Alright, so this is a computation using a known formula, the point on 2 lines theorem. And that tells us exactly what the 2 components are as 2 ratios of sort of determinant-like expressions obtained from these 6 numbers. Okay, so first of all, the denominators are formed by taking this term here times this term minus this term times this term. And the numerator of the first term is exactly the same as that, but instead of using the first components of each vector, we replace them with the third components. So instead of having this times this, we now have this times this minus this times this. That's exactly what's appearing here. And what about the y component? Well, it's also the same. It's really the same as the denominator, except that instead of using the middle terms, we replace the middle terms with the final terms. So the numerator here should be 1 minus t1, t2, not times this, but rather times this, minus this 1 minus t3, t4 times this. So if you calculate 1 minus t1, t2 times 1 plus t3, t4, and then you subtract 1 minus t3, 4 times 1 plus t1, t2, then you'll see that you're going to get 2 times t3, t4 minus t1, t2. That's that relation that I just wrote down there. So with these preliminaries under our belt, we can now tackle this duality in coordinates theorem. So here's the setup that we need to examine. Let's start with 4 points. ET1, ET2, ET3, and E of T4 lying on our null circle. Those 4 points determine 6 lines. There's one, there's another, there's another, there's another, and then there are these 2 as well. And those 6 lines meet 2 at a time at 3 other points. Let's call them D, F, and G. So our notation here in terms of previous notation is D is the place where this line and this line meet. So that was E of T1 and E of T2, and where E of T4 and E of T3 meet. So D is equal to M of T1, T2 and T3, T4. F was the meet of these 2 lines, so it's M of T1, T3 and T2, T4. And G is the meet of these 2 lines, so it's the meet of T1, T4 and T2, T3. This is an interesting and good example of what I might call threeness from fourness. Okay, so you have 4 things. In this case, the 4 points on the null circle, but it doesn't really matter what they are. And from this collection of 4 things, you want to get 3 things. So you might think that 3 and 4 are somehow incompatible. But in fact, there's this lovely and simple way of going from fourness to threeness. How? Well, we've seen it here. It's thinking about subdividing these 4 points into 2 groups of 2. All right, that's one way of doing it. Another, that would be like that. Another way of doing it would be to group those 2 together and these 2 together, like that. And the other way would be to group these 2 together and these 2 together, like that. So in terms of those 4 points, you could group the T1 and T2 together and the other ones, or the T1 and the T3 together and the other ones, or the T1 and the T4 together and the other ones. There are 3 ways of grouping 4 things into 2 subsets of 2 each. And those 3 ways correspond exactly to these diagonal points of the original quadrangle. Okay, so there's our notation. Here's our theorem that we're trying to get at. That if D, let's say we have to choose 1 point. It was A originally, let's call it D now. If D happens to be x0, y0, then D perp is x0, y0 to 1. And what's our definition of D perp? Well, it's exactly coming from this situation here. It's what you get when you start with D, construct these 2 lines first, then construct the other lines, finding F and G, and then finally joining F and G. So what we're going to do is we're going to, here's the idea of the proof, we're going to express D, F, and G in terms of T1, T2, T3, and T4. We know exactly how to do that using that rather long expression on the previous page. Then we're going to write D is equal to, say, x0, y0. We're going to call the 2 components of D x0, y0. And then we're going to show that F and G, these 2 points, always lie on this particular line, x0, y0, 1. Whatever the coefficients here are, we're going to use those coefficients to cook up this line, and we're going to show that this F and this G lie on that line, which means that this actually is the line through F and G. And it's going to be so independent of what T1, T2, T3, and T4 are. This line only depends on where D is. It only depends on the coordinates of this point, not on T1, T2, T3, and T4. So even though F and G depend on T1, T2, T3, T4, the line determined by them is only determined by D. That's our strategy. Now we actually have to get down to the nuts and bolts looking at the coordinates of D, F, and G in terms of these four parameters. Okay, so here's a real challenge for us now, to come to grips with this crucial argument. This is the crucial argument of duality, of really establishing the existence of the pole-polar duality, going right back to Apollonius. But we're doing it in the Cartesian coordinate framework. Okay, so there's our point D. Its coordinates we're going to call x0 and y0. We know what they are in terms of t1, t2, t3, and t4. That's just what we established. There's x0 and there's y0. What about f? Well, f, let's call it x1, y1. That's the meet of t1, t3 with t2, t4. So exactly the same formula, but with the roles of t3 and t2 interchanged. So these two, just the same as those two, except that wherever we have a t2 here, we now have a t3. Wherever we have a t3, we now have a t2. What do we need to do? We need to check that this point F lies on this particular line, x0, y0, 1, which we're claiming is the dual of D. And what does it mean for F to lie on this line? Well, it means that the coordinate x1 and the coordinate y1 satisfy the equation x0 times x1 plus y0 times y1 equals 1. We need to check that this is true when x0 and y0 are this, and x1 and y1 is that. Okay, how are we going to do that? So we have to multiply this x0 times this x1. And then we have to multiply this y0 times this y1. Looks like a big headache. But let's not panic. Let's look at it carefully and rationally. What's going on? There's a denominator that appears when you multiply x0 times x1. This term here, the denominator here, times the denominator in x1. That's going to be the new denominator of the product. But that's going to be exactly the same as the denominator of y0 times the denominator of y1. Because these two denominators agree and these two denominators agree. So these two things here have the same common denominator. Why don't we just multiply it through by that common denominator, getting it up to the right-hand side. Then what we need to check is much simpler. There's no more fractions at least. Okay, so we're going to multiply x0 times x1. And we're going to multiply that through by that common denominator. So it's really just the numerator here, which I've copied right there, times the numerator of x1, which I've copied there, and then plus the numerator of y0, which I've copied here, times the numerator of y1, which I've copied here. And all of that should equal this common denominator once it's brought to the right-hand side. And so that one there is the denominator of x0 or y0, and this one here is the denominator of x1 or y1. Okay, so what can I say? At this stage, we need to check whether this is true for every t1, t2, t3, and t4. This is an identity. It means that it's true, and that you verify it's true by, well, lacking anything else, just expanding the left-hand side, expanding the right-hand side, and observing that those two sides of the equation are term by term match upable. They're exactly the same. And it's a little bit remarkable, isn't it? I think it's very pleasant. If you just looked at it, maybe you could find some clever way of seeing it, but it's probably easier just to multiply it through and gather like terms and see that the left-hand side really does equal the right-hand side. So that's the proof of that. It comes down to this identity. And we're going to see that's a common theme in universal hyperbolic geometry. That profound things, or deep things, come down to identities, which are often rather complicated. This one's reasonably complicated, but it's not as complicated as some other ones that will appear. So we've proved now that the point F lies on this line here. And, okay, what about G? Well, G is the same kind of story. It's really just a variant on this. If you like, you can try it out. Just check that the point G also satisfies exactly a similar kind of identity. So both F and G lie on this line. And so the line through F and G, which is the dual of D, must be equal to that. Now that we understand duality, we also understand perpendicularity, either between 2 points or between 2 lines. Because perpendicularity in the hyperbolic geometry is defined in terms of duality. So we can state this very useful perpendicularity in coordinates theorem. The points A1 and A2 with coordinates x1, y1 and x2, y2 are perpendicular precisely when x1, x2 plus y1, y2 minus 1 equals 0. And the lines L1, M1, N1 and L2, M2, N2 are perpendicular precisely when L1, L2 plus M1, M2 minus N1, N2 equals 0. So proof. The first part. The 2 points are perpendicular precisely when A1 lies on the dual of A2. Or conversely, A2 lies on the dual of A1. But we know now what the dual of A2 is. If A2 is this point, then its dual is the line x2 to y2 to 1. And A1 lies on that line precisely when x1 times x2 plus y1 times y2 equals 1. And that's pretty well what we wanted to prove, except we just got everything to the left-hand side there. The second part, we have 2 lines. And the 2 lines are perpendicular, by definition, precisely when L1 passes through L2 dual, or conversely, when L2 passes through the dual of L1. Well, what's the dual of L2? So we have to go in the opposite direction from the duality in coordinates theorem. If we have a line like this, we'd rather express it with a 1 in this third position. And we can do that by dividing by this third component, n2, provided that third component is non-zero. Let's suppose that it is. So we divide by n2 and rewrite this as L2 over n2, m2 over n2, 1. In that case, we can immediately read off what its dual is. It's going to be L2 over n2, m2 over n2. Now the condition that L1 passes through this is the same as saying that this lies on L1. That happens when L1 times this plus M1 times this equals N1, which is right there. And multiplied by N2 gives us this here, which is what we want to prove. Well, what happens though if N2 is 0? Then we're not allowed to do this. But then we can reverse the roles of L1 and L2, and we can apply the same argument with N1 instead of the N2. Okay, that's fine. What happens if both N1 and N2 are 0? I'm going to leave that to you as an exercise. So as an exercise, prove the story that in the case when both N1 and N2 equal 0 separately. Later on, when we go to the projective point of view, this kind of special finicky fussing around about whether something's 0 or not is going to be much less of an issue. It's one of the reasons why we want to move ultimately to the projective point of view. Okay, so now on to the quadrants in coordinates theorem, which says that if A1 is x1, y1 and A2 is x2, y2, then the quadrants between them is 1 minus this expression, x1, x2 plus y1, y2 minus 1 all squared, divided by x1 squared plus y1 squared minus 1 times x2 squared plus y2 squared minus 1. We're starting to see this kind of expression quite often. Okay, so we need to recall some basic things. First of all, the definition of quadrants that we've so far adopted is as a cross ratio of 4 points. Which 4 points? Well, let's say here's A1 and here's A2. There's the line A1, A2. The dual of A1 is some line A1 perp. The dual of A2 is some other line A2 perp. They meet the line A1, A2 at these new points B1 and B2, which we might call conjugate points. And in terms of B1, B2 and the original A1, A2, the quadrants was defined to be a cross ratio. The cross ratio of A1 to B2, A1, B2 to A2, B1, in that order. Okay, so first of all, A1 and A2 are those 2 points. The line joining them is this expression here, which we've already seen. The dual of A1 is this expression, this line. That's that line there. And the dual of A2, that's that line right there. So that's from our duality and coordinates theorem that we've just proven. Now we want to get at these conjugate points, B1 and B2. Well, there's B1. And there's B2. And how did we get this? Well, we just use the fact that if we know 2 lines, this line and this line, then we can write down the coordinates of the point that they meet at. So for example, B2, A1, A2 is that line right there. A2 perp is that line right there. So it's a question of finding the meet of this line with this line. And the meet of 2 lines theorem is exactly a formula for that. And you can check, hopefully, that I've done it right, that I've done the right combination to write down the 2 conjugate points. So now we have all 4 points at hand, and now we can try to compute this all-important cross ratio. The cross ratio A1B2 to A2B1 is a ratio of ratios. The first ratio is between 2 vectors, the vector A1, A2 and the vector A1, B1. And we have to divide that by a similar kind of ratio, the ratio between the vector B2, A2 and B2, B1. Okay, so let's start by looking at the numerator. How will we evaluate that ratio of vectors? Well, each of those vectors has an x and a y component. And if we want to compare the ratios of the vectors, it suffices to compare the ratios of either the x components or the y components. So let's suppose, for the sake of argument, that x2 minus x1 is not equal to 0. In other words, that in this numerator here, the x coordinates of A1 and A2 are different. If they were the same, then we would have to do this argument with the y components. We would look at the y components of everything, but we're going to look at the x components of these 2 vectors. So the x component of the vector A1, A2, it's going from A1 to A2, so it's the x component of this one minus the x component of this one. It's just x2 minus x1. The x component of this vector, well, it's the x component of B1, which from the previous page is that thing, minus the x component of A1, which is x1. Okay, so we need to do some more algebraic manipulation here. We've got, there's the main line of the fraction. There's the numerator, and this denominator is itself a fraction minus x1. So we're going to get this first over a common denominator by multiplying through by this denominator here, this times the x1, and combine that with this thing up here. Now when we do that, the denominator that's here, because those whole fractions in the bottom half of this big fraction, when we divide by this fraction, it's the same as multiplying by its reciprocal. So the thing that's in the denominator here is going to end up in the numerator of the final result. And that's where this term here comes from. x1 squared plus y1 squared minus x1, x2 minus y1, y2. That's just this term right here. That's going to end up in the numerator along with this x2 minus x1 term, which is already there. Okay, and then the rest is going to be what you get when you combine this with x1 times this. Okay, you can just expand those terms out. Those terms minus x1 times this, and you get these terms right here. Now something pleasant happens is that this x2 minus x1 factor up here also divides this new denominator, because it divides that term, and it also divides this term here. This is together, this is x2 minus x1 times y1 squared. So let's just get rid of all that x2 minus x1. So it disappears from there. And here we're just going to be left with y1 squared with an x1 squared and a minus 1. And our numerator achieves this relatively pleasant, simple form. We're happy. It seemed like it was going to be complicated, but it's simplified into something that's familiar to us. In particular, this term here is part of the final answer, so that's good. So as an exercise, maybe it's exercise 6.2, do the case when the two y's are not equal to 0. If you want to, same kind of reasoning, just looking at y components instead of x components, you should get the same expression. All right, so what about this denominator? b2a2 over b2b1. Well, I've written the x component of b2 minus the x component of a2. I'm allowed to do it the other way if I do the same thing here. The x component of b2 here minus the x component of b1 here. We have to simplify this. So there's fractions top and bottom. This denominator here is the same as this denominator here. What we should do is we should multiply top and bottom by the product of this denominator and this denominator. That will clear the fractions from the top and from the bottom. This one here is just this term that we've already seen, x1 squared plus y1 squared minus x1, x2 minus y1, y2. So when we multiply that, well, it's just going to be up there. When we multiply by this one here, this term here will drop out, and we're just multiplying this by x2 and subtracting it from what's up here. So we need to take this term here, all these things up here in this numerator, and subtract x2 times this term here. So that turns out to be x2 minus x1 times x2 squared plus y2 squared minus 1. You might like to check that. So this minus x2 times this has x2 minus x1 as a factor. And the remaining thing is x2 squared plus y2 squared minus 1. Okay, that's what's happening on the top. What's happening on the bottom after we've multiplied by this common denominator here? Well, we have to take the numerator here and multiply it by this denominator and subtract the numerator here multiplied by this denominator. That's what I've done over here. That's what all this is. So there's the numerator times this denominator minus this numerator right here times this denominator right here. Oh boy. Okay, so you have to multiply this times this and subtract this times this. All right? Get out a pen, paper, write all down, simplify. We end up with this expression. Those are all the terms that are left in the denominator. Okay, well, it looks difficult, but it turns out that miraculous things almost always come to our aid in this subject. And the miraculous thing that occurs here is that this rather complicated thing in the denominator here is actually built up from relatively simple things. It's really x1 squared plus y1 squared minus 1 times x2 squared plus y2 squared minus 1 minus x1, x2 plus y1, y2 minus 1 all squared. Okay, maybe that's not so obvious. It isn't so obvious, but it's true anyway. So that the denominator simplifies to that. So what happens now when we take the numerator that we calculated on the previous page and multiply by the reciprocal of this denominator here? Well, some cancellation takes place. This term here appeared in the previous numerator. When we multiply by the reciprocal of this is exactly going to cancel with the one that we had before, so they're going to disappear. The other thing that we had in the other one was a term just like this, x1 squared plus y1 squared minus 1. That's going to end up in the denominator along with this thing here. And the new numerator is going to be what's here. So it's going to be this thing here times this thing here minus this thing all squared divided by, well, essentially divided by this thing. That's the net result of taking the numerator and the denominator and dividing one by the other. And what you get when you take this and divide by that, you get 1, because that's going to be 1, minus this quantity squared over this. That's exactly our formula for the quadrants between the 2 points. Now all that remains is the spread in coordinates theorem, which is very similar to the quadrants in coordinates theorem and follows from it pretty simply using duality. So we have two lines L1 and L2 with these coordinates as before, and the claim is that the spread between them is 1 minus this expression here. Let's assume that N1 and N2, the third components, are both non-zero. In that case, we can write down what the duals of these lines are. The duals of the lines are what you get when you divide by N1 and N2 and just look at the first two components. L1 over N1, M1 over N1, and L2 over N2, M2 over N2. Now the spread between the two lines L1 and L2 is the same as the quadrants between the dual points. And that's the theorem that we've just proven. That's 1 minus, okay, here is the expression in terms of these things. This times this plus this times this minus 1 all squared divided by this squared plus this squared minus 1 times this squared plus this squared minus 1. And now in this expression here we multiply top and bottom by N1, N2 all squared. So this becomes L1, L2 plus M1, M2 minus N1, N2. And this one becomes L1 squared plus M1 squared minus N1 squared. And this one L2 squared plus M2 squared minus N2 squared. And I'm going to leave to you as an exercise to find an argument for the cases when N1 or N2 are 0. Alright, so I admit this was a heavy lecture. It's probably one of the hardest lectures in at least the first part of this course. And don't worry overly if, you know, a lot of it was a little bit too complicated for you. I want to present a record of the proofs of the theorems that I'm claiming, and so it's something that you can check if you want to, and if you want to practice your algebraic skills, it's a pretty good way. We've seen, however, that this approach suffers a little bit from a same kind of problem that's bedeviled Euclidean geometry for many hundreds of years. The problem is that parallel lines present a particular challenge in coordinates, because the formula for the meets of two lines breaks down when the lines are parallel. 17th century geometers realized that one wants to add points at infinity somehow to make that problem go away, to make problems like this go away. So that's projective geometry, but it really only came in clearer focus in the 19th century. We're going to adopt a projective point of view, and then we're going to have another look at this whole setup. We're going to see that in fact it can be simplified dramatically. So projective geometry is the key to making formulas really become beautiful. So next time we are going to start with an introduction to projective homogeneous coordinates. And we're going to see how some of these ideas translate very pleasantly into that more general but much less familiar picture. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.